All right, so we're looking at page 3, and it's all about them mechanisms. All right. Starting at the top, we got an ester, and we're under aqueous acidic conditions. Sorry, my microphone just got caught on something. So we have an ester, we're under aqueous acidic conditions, and kind of, maybe the first thing to do with this is to, know what the product is. So you can kind of treat this as a fill in the blank, right? We need to know where we're going to end up, right? Here's where we start, right? And we need to know where we end. So it's always a good idea to draw the products, right? So if we hydrolyze an ester, we know we're going to make the carboxylic acid and we're going to make the corresponding alcohol, right? And if we wanted to, be, um, complete about this, I guess we could, fill in some colors here just to know where everything comes from, right? Right. So the purple and the red, right? Those are the pieces that are coming together. If we really kind of knew it all in our heads, I guess we could say that that OH there sticks with that aryl group, but then this OH here is coming from the water or the acid here. But it's okay. We'll get to that kind of gritty detail here in a minute. But it's always a good idea to know what leads to what, right? Where you start and where you end. It's hard to kind of run through a mechanism if you don't know what the end product is. So that would be my suggestion on how to start this. Okay. So I'm going to abbreviate this as pH, just as phenyl, just to keep things um, in check. Okay. So we start out with this, and we're under acidic conditions. So H plus it up, all right? Under acidic conditions, that means we're going to be protonating that carbonyl oxygen, right? We have to give a good reason to attack that carbonyl carbon right there. Right now, it's positive-ish, right? But it's definitely not positive enough for, a weak nucleophile like water to come in, right? So we have to give it a good reason to start it out, and that good reason comes from protonation of that carbonyl, which sets up, right? Which sets up a positive charge. And the whole point of this, right? The whole point of this is that we can draw a resonance structure, which helps to emphasize the point that right, we now have a complete positive charge on that carbonyl there. Although remember, this is a resonance, right? But the point is that if we can draw a resonance structure where we have a positive charge on that carbonyl, a full positive charge on that carbonyl, right, it's more susceptible to nucleophilic attack, right? This one is the more correct resonance structure, right, because it's got the more complete octets for everything, right? We've got more bonds, it's more stable, right? But this might be the one that we would say is, I guess, more reactive. I mean, that's kind of a debatable idea there, right? But either one of these is okay, right? This one is the one with the check marks, the more technically correct one. So we're going to continue from that. Now that we've given our carbonyl carbon a more positive charge, now we can send in a nucleophile, right? So I'm just going to mark over that in red there. Okay, there we go. Now we can bring in a weak nucleophile like water, and that will be okie dokie to continue along. There's this. We brought in this here, okay. All right, so we protonated our carbonyl oxygen. We brought in a nucleophile. We slammed open our pi bond. Now we want to close our pi bond, but we need to make a good leaving group, right? So let's make a good leaving group. We're going to protonate our oxygen here, and we'll just do a little internal protonation action right there, okay? So let's draw what this is afterwards. So here it is, pH, O, That should have been in red, excuse me, red, to my yellow hydrogen that I plucked from my incoming water group. That's bound to here, bound to here, bound to here, bound to here, here, and here, okay? Now we've got a good leaving group. Let's make the magic happen. Let's make it leave, slam down pi bond, kick off the best leaving group, right? Okay. And then what do we have left over? We've got this, 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 here, here, and we made a purple pi bond, got our positive charge. So let's bring in some water and just finally clean everything up. Sorry, let me stick with my colors. Done and done, right? All right, I'm going to try and move this stuff because it kind of got in the way here. All right, so there it is, right? The classic acid hydrolysis of an ester. Cool. All right. Next, we've got another ester, but now under basic conditions, right? So here's where we start. Do you guys remember where we end, right? So if you want to take a quick pause and say what happens under base conditions for an ester, right? Base conditions for an ester, what's our product going to be? So take a quick pause, see if you guys can come up with it, and then come back. All right. So let's put some color with things, right? And I'm just going to generically put these guys in blue. So we've got 1, 2, 3, 4, right? We've got 1, 2, 3, 4 carbons. We know that they're not going to go anywhere, right? We're not going to get rid of. Right? So we know our product's going to end up like this, right? Under base catalyzed conditions, right, we're going to split open. We're going to split open our ester, right? We're going to split, excuse me for just a second. All right, so we're going to split open our ester and leave us with a carboxylate and an alcohol. And we'll talk real quick about what's going on with that carboxylate there, okay? But so as with the acid catalyzed hydrolysis, right, we're going to be breaking apart the ester, right? We're going to be breaking it apart. This time we're doing it under basic conditions, right? Okay. So let's get it going. Now, we don't have any acid in this case, but we've got a much better nucleophile, right? We've got this OH. So it can go ahead and whoop, do that right there, right? So it's going to come in. Let's fill in the colors. Purple, blue. We brought in a black OH, right? And this was here. We'll make that one in blue too, okay? So that's what happened after this first step, right? We brought in the OH and attacked the carbonyl. Carbon popped up to make a negative charge, okay? So we sent up the pi bond. We need to send it back down and kick something off. So we'll kick that off right there, okay? Now I'm going to draw this purposefully like this, just so we can, let's say, visually, it'll be a little bit easier to kind of keep track of things. We made that there. Okay, so you guys still with me? Right, and there's my negative charge that came from that, right? Okay. Now we got a negative charge. We got the beginnings. Well, let me draw this real quick, right? We got a carboxylic acid here so far. That's not really going to hang around, right? As soon as under basic conditions, that negative charge is not going to hang around. So let's just send in and deprotonate this here. Trying to just keep it all together. Red to pick up a black hydrogen there. Blue here with a red there. And another. Okay. And if I clean it up, right, if I straighten this out and make it linear, then we'll get to our product up there, right? Not too bad, right? You see a lot of similar steps as we did under the acid catalyzed formation, but clearly in this case, right, we don't have any acidic hydrogens to begin our process with.